So before I plotted V, and let's just put T, so I had a bell curve for T in specific volume. I can do the same thing, but plot T versus H, the enthalpy. I still have a bell curve. And now this difference between here and here is the latent heat of fusion. Or excuse me, latent heat of vaporization. So this is the enthalpy of my fluid when it's just pure fluid, of pure fluid at a given temperature. And then over here I have the enthalpy when it's all 100% vapor. So if I have a mixture of 50% liquid, 50% vapor, I can just look this up. I can look up the latent heat of vaporization. Latent heat of vaporization, I have that. Yes?
Is that for like finding the sweet spot of like fuel-air mixture for combustion? Is that kind of what you're getting at here? Like there's a certain mixture of, maybe not even with the air, but like a certain mixture of liquid gasoline and vaporized gasoline that will burn the most efficiently. Is that the goal of that?
Well, I would say that thermodynamics applies to that. I'm not sure, I don't know, I can't answer your question and give you an example of how this applies.
Okay.
But I would say if there's an ideal mixture, now you're talking about air-fuel mixture.
Well, I think, yeah, I know that exists, but I don't know if there's
So air-fuel mixture is different than liquid fuel, vapor fuel mixture.
Right.
So what we're talking about here is a material and liquid state, material and gaseous state mixture.
Okay, so even if without a specific example, you're saying, though, dependent upon what the mixture is, there's properties that will change.
Mm-hmm.
Okay.
So when I did this, okay, and I plot T versus H, if I'm going to take a liquid and I'm gonna take a pot of water and I'm gonna boil it, and I want to know how much energy I have to put in to boil that water. I know I start with, and I say I start with water at 25 degrees C, and this is 100 degrees C. So I start with water, it's just above this curve, okay? So I start with water at 25 degrees C. And I have to heat it up to 100 degrees C, but it's still liquid. So there's some energy I need to put in to heat it up to 100 degrees C. Then I have to go through a phase change and go from 100% liquid to 100% vapor. This has it's small h, so it's units of energy per unit mass, kilogram, okay? So if I know the total amount of mass, I can make this big H. So given that, I know the total amount of energy it requires to take my 1 kilogram of water at room temperature and heat it up to 100 degrees C and then boil it all into vapor. So this gives me the amount of energy required to go through a phase change. I could replace this with entropy too. The curves move around, they skew a little bit when I go from enthalpy to entropy, but it's still bell curves. Whether I have small v, u, h, right, or s, they're all bell curves when I'm dealing with liquid vapor mixtures. And going from here and here tells me something about the energetics associated with the phase change.
So the quality is how far you
The quality is if I'm 100%. It tells me the total amount of vapor in my mixture.
So if you're at your quality number, the X number is 0.5.
I'm in the middle.
You're in the middle, and you only need that much more to get there. Okay, got it.
But if my quality factor is 1, I have 100% vapor, so I know I'm going to be along the saturated. So if I tell you the output of your turbine has a quality factor of 1, and the turbine, I'm telling you the turbine outputs water vapor, then you know that you have to be along this line. Because all of this is x equal 1. And I might ask you, tell me solve for the temperature of the vapor leaving. So if you knew how much power was coming out and the energy you put in, you could calculate the energy consumed, and so then you would get some value for energy, and from that you could tell, you would know where on this curve you were. I'm just pointing out, though, if I tell you the vapor quality is 1, if I tell you the vapor quality is 0, and I tell you you're dealing with liquid vapor mixtures, you should always kind of get an idea about drawing a curve like this. Okay, so before I move on to the next part, I just want to point out, so if you work for a gas company, okay, natural gas company. So when I think after high school, I worked for a natural gas company, and this is after I started physics. And I remember going into the control room where everybody, so I was just picking weeds and stuff, right? But nevertheless, going into the control room, they had all these computer screens up, and they had plots, and they were showing points on like curves, and they were monitoring at different stages on the glass line, and they just had some curve up there. I remember that, man, that looks goofy. But they had these different points, and then they had this, they were like, it was populating with like, like throwing paintballs or darts, right? And you get a mark everywhere the dart hit. And they were doing this. And then later on, many years later, after I learned some of this stuff, then I was at a control room for refrigeration system. And then they had a plot like this. And so what ends up happening is they know they're dealing with a given material, and they know it can be in liquid state or vapor state. They're dealing with compressions and temperatures. And they know when the system might break down. And so there's some operational regime. And so there might be some operational regime where this is the window of operation. And at some stage in the process, they should be here. And so what they'll do is they'll plot out the properties they expect, and then they'll be updating what is the temperature. Now, they won't use enthalpy, they'll probably use specific volume. They'll be plotting out the pressure and specific volume and temperature of specific volume at that point. And if they suddenly start getting dots out here, they know to hit a red button to shut it down because they're way outside their operational regime and things are going to damage. There's something going to be a breakdown. So when you're dealing with liquid vapor mixtures in operational type processes, typically they'll have some operational regime or some cycle which the system should be working in, and they'll be populating where they are at different stages in the cycle, and they'll be making sure that all things are going properly. And then by putting this curve on here, it's just really intuitive to know, okay, we're having problems during some compression cycle or with some phase change part of the process. So there's different stages, so we know we might have a leak because we have, or I don't know, in this case we'd have too much heating. So maybe our insulation's, if we're supposed to be here but we're way out here, that means we're heating it up way too much. We have more superheated vapor than we should expect, so maybe we have some insulation problem. Now, if we're getting points down here, it might be a little bit different. Then that would suggest that maybe we have both a leak, probably more of a leak. Okay. So related to that, so this is a saturated water temperature table. And so right here is the temperature, and I just underlined 100 degrees because we know water boils at atmospheric pressure at 100 degrees. And then right here is the saturation pressure. And so 101.3 is 1 atmosphere. So we always say at atmospheric pressure, water boils at 100. But really, it's slightly different. But if I have water at 100 degrees, then the pressure associated with boiling is going to be, and so this is 1 atmosphere. Okay? And so at this temperature, given that I know the saturation pressure, now I can have water at 100 degrees C, but I could have water within a pressure cylinder. So I could have a lot higher pressure than 1 atmosphere. So in this case, we're more talking about water at 100 degrees C, like on your stove boiling. Okay, so then I can get the specific volume in the fluid. So this is the specific volume in the fluid. This is the specific volume in the gas. So if I go back to one of these curves, just pop it up there real quick. If I put T here, 100 degrees, I just looked up this value in that table. I just looked up this value on that table. I'll circle them in red. Okay. Now, let me pick out 110 degrees, and I'll do this. And if you look here, the saturation temperatures change a little bit, but or saturation pressure. And so now I just picked this, VF and VG. Now I go back over here. Now I went to 130 degrees C. And I have these points. There and there. Increase the temperature. This one got bigger. This one got smaller. The width of my difference between VF and VG got less. If I go to lower temperature, the width increases. So you can see, if I just plot temperature versus these values, I can reproduce the bell curve. Now, this was for a specific volume. I can do internal energy. Okay, and so I have UF, UFG, UG. So then related to that, 419 kilojoules per kilogram. VG, should be a little bit better. So I have 419, I have 2500. If I take this, subtract this, that's what I get. This is the width of the curve. So if I instead I plot temperature versus U, then I get a bell curve. And if I compare these two, and I'll just put a box around it, you can see at lower temperature, UFG, the width of my curve is greater. Lower temperature, it's greater. So if I go back to here, I replace this with U, I still have a bell curve, increase the temperature, goes like such. And then I could go all the way up to the critical point, and at the critical point, this number would approach 0. So as I went down, and it went to higher and higher and higher temperature, at some point my width of my bell curve would go approach 0, and then basically it would be 0, and I wouldn't be able to distinguish whether it's internal energy of fluid or internal energy of gas, because my fluid has a split personality. So I can do that with this, and then of course I can do the same with H. So now at 100 degrees, I have my enthalpy here. So HF, HFG, HG. So I have that, and if I subtract this from this, I get this number, HFG. And so let's just circle these. And so you see, as I go to higher temperatures, this number decreases. So if I plot T versus H, I have the same type of thing, but then I would have HF, HG, HFG, and HFG would approach 0. So HFG, when I said in words, is the latent heat of vaporization. So the amount of energy required to go through a phase change. So as I get higher and higher the temperature, approach a critical point, there's basically no energy associated with vaporization. So typically we just, when you look up, oh, there's a latent heat of fusion, latent heat of vaporization, and then you see a number, right? 2,300 kilojoules per kilogram, okay? For the latent heat of vaporization of water. And you see that number. Well, no, it's not 2,300. I'm glad I got the number pretty correct. I was just saying off the top of my head. But it's not just, 2,300. It's dependent on the temperature and pressure. So given that in thermodynamics, we like to talk more about, equations of state, temperature and pressure. So now they use HFG because really the latent heat of vaporization is a function of temperature and pressure. And this bell curve represents that perfectly. If I plot temperature versus H, my HFG up here is much smaller than it is down there. Any questions on this? So I'm just kind of outlining. I used to ask students to reproduce bell curves and stuff like this for homework, but class sizes have gotten too large, so it's too hard to grade. But I would say a good exercise for you to do is just to reproduce a bell curve. Or a really good exercise to do is to pick water, produce the bell curve in terms of temperature and entropy, and then take one of the new refrigerants that they're using for some new technologies, and then plot it. And then what you'll find out, if you plot temperature versus entropy, you'll get something that looks like this, a bell curve like that. And then if you pick one of these special fluids that are being used, that they want to use in data centers for certain purposes. So now with the cloud and all this other stuff, now there's a lot of money going into paying for these big, computer data centers. And then if you pick one of these new things, you'll get something that will look like that. So you can see that it's a lopsided bell curve. But you can do this for water vapor and you'll get something that looks like the black line. Then if you pick something other than water, you pick some fancy refrigerant, and you plot, you'll get some funky curve that looks like this. And you can see now that it's highly anisotropic, you can probably play around with it for a certain purpose. It's going to have its pluses and minuses. So as soon as you start having curves that look like this, you can see if I have my operational regime. Remember how I drew a box? You can see I can go from liquid to vapor really quick instead of just being hot vapor versus vapor. So you would see that you're operational, so you might have better performance, but much stricter standards on making sure that you stay within those operation regimes. Because if you have a certain stage where you only can have vapor, but it's starting to become liquid, you might have a lot of problems versus just hot vapor versus vapor. Any questions on this? I'm trying to introduce this table and how it applies. Yes?
So the whole point of this tape was to be able to produce the bell curve?
No, that's an exercise. The point of the table is so you don't have to use the ideal gas law to tell you what the specific volume is at a given temperature and pressure. The whole point is so somebody else did all the work for you, so you know exactly what the internal energy is, what the enthalpy is, what the entropy is. Somebody did all this work for you, so you can give me a 50% estimate on the energy required to do something using water and water vapor. Because you don't have to look up any properties. All you need is the first law, the second law, and some other knowledge with these properties, and you can do all the calculations you need. But if this table didn't exist, how long do you think it took somebody to do this accurately? Quite a while. There's a lot of points here. So you could see if you wanted to get your engineer and they say, let's use a new fluid. Well, wait. We don't even know what the properties of the fluid are. So they have to spend all this time making sure the properties of the fluid are right before they even can do calculations on what they project the efficiency would be with the new fluid over the whole operational regime. So this allows you to calculate the expected efficiency based off of engineering design change. So that's the real power. You have all these equations of state provided for you. Okay, so just as a side point, I'll finish here. So, okay, now this is a pressure table for saturated water. So now I list the saturation pressure. So 101.3 is 1 atmosphere. And the saturation temperature is 99.97. So water really, at 1 atmosphere, pure water really boils at slightly under 100 degrees. So if I reduce the pressure, so I go to the top of Mount Everest, so the pressure at the top of Mount Everest is about 20 kilopascals. Water boils at 60. So 60 degrees C, what is our body temperature in Celsius? What? 35 degrees Celsius? What's that? 37? Okay. What's that? Okay. I thought it was higher than that. I thought it was more like 50. But anyways, okay, so let's say it's 37. So this is 60 degrees. So now let's say we go to Mars. So this is a funny thing about when they talk about space travel. What really kills you is all the fluids get sucked out of your body. It's the pressure that kills you. It's not the gases, toxins. It's the fact that as soon as you open that suit, you become a tomato put in an instant dehydrator at, it basically explodes and all the liquids get, you dehydrate food, right? So if I go to Mars, it's really low pressure atmosphere. You have to go in the real deep valleys. So that you have water in your body, or 90% water, whatever. So if we step outside, all the water in our body wants to boil. Gets sucked right out. Doesn't want to be water vapor. Because the saturation temperature is well below. So if I go to the top of Mount Everest, all I have to do is heat my water up to 60 degrees C before it starts the nuclear boil. If I start going to the bottom of the ocean, say down here, then I need much higher temperatures to boil. So there's an interplay between temperature and pressure. So the saturation temperature, saturation pressure. If I know the pressure, then I can look up the saturation temperature. If I know the temperature, I can look up the saturation pressure. We usually just do a lot of reference to this region right here, atmospheric temperature and pressure.